Hello guys, can I do a sound check? Can you guys hear me on your side? If it's okay, can you let me know with a reaction button, thumbs up or something? Okay, great. So we're waiting for people to enter. So once you're in, do the same thing. Okay, help me switch on your webcam so I can see your beautiful, handsome faces. Right. Also, let me know if you can hear me by giving a reaction button, thumbs up. Okay, thank you for that. Okay, good. All right, good to see you guys. Now, you notice one difference, right? Today, I'm running alone. Okay, actually, Mr. Yap, he's supposed to be here, but then one of our teachers is not well. So Mr. Yap is being deployed towards Balmoral Plaza. So he's teaching one of the classes. That means I'm the only one that's left. So no worries, I'll be running through the lesson together with you. Right, so later, if you have any questions or what, you can feel free to send questions to me. I may not be able to reply to you immediately, but I'll do whatever I can, right? So we just try to work together. Now, as people are still strolling in, right, maybe I just want to start today's lesson by doing a simple poll question. You know, your lesson has already begun for 1 week. So I just want to find out, how's your first week in school? Tell me more a little bit through this poll question. Okay, I see a lot of tiring, a lot of grades, okay, which is not too bad. Okay, I'm just trying out my poll, okay? Once you can see the poll question, just click to make sure that I know everything is okay on your side. Okay, I think not too bad, right? I'm going to end the poll very soon, okay, in about 5, 4, 3, 2, 1. Okay, I'm going to end poll. I'm going to share the results with you guys. Okay, so you can see most of you guys says that it is tiring, about 50% of you guys. Then 41% says it's great. Only about 10% of you guys, I don't know what happened in school, rather not talk about it. It's okay, right? You're just starting your first week of many, many more weeks to go, right? So try to get used to JC. It's very different. I've spoken with a few students. The first major difference is everything is very self-directed in terms of learning, right? So you will notice you have to go and watch your own lectures, do your own tutorials. There's no one that's really pushing you. So the only person that really can push is yourself, right? So do stay focused and please know why you entered JC in the first place, all right? Okay, very good. So I think most of you guys are already in. Okay, and also last week my mic was not working, so I couldn't really hear you guys speak. Okay, so I think I have fixed that today. I just want to test, okay? And let me just look through your beautiful faces. Okay, I can see Sheng Kai. Sheng Kai, are you there? Okay, good. Thank you for waving, right? Okay, can you just say a hi to me? I just want to hear your voice. Make sure it's okay.
Hi.
Hi, okay, great. Very sexy voice. Everybody can hear Sheng Kai. Okay, so later I'm going to ask you guys to unmute, all right, so that we can have a bit of conversation here and there, right? Also, along the week, for people in our classes, we did ask them, how was the Zoom session for you guys? Anything that we could have done a little bit better? If you ask me, right, I am a person who doesn't like to Zoom, okay? Honestly, I think it's very hard to teach over Zoom. Not like in class, when you do questions, my style is I like to move around. I like to watch you do questions. Over Zoom, it's like very hard. I don't even know what you're doing, right? But there's convenience, obviously, but it's very hard to really run classes over Zoom. So this year and last year, there's COVID. So it's very hard for us to also pack all the students together. But I think the restrictions, they are easing. So I do foresee that maybe in the near future, if we do run events like this, we can invite all of you back into class. Then we have all our teachers. Then it will be a very nice event. Okay, it's okay. We'll just make do with whatever we have. So remember, there's always consultations, Telegram. If we are not clear in one way or another, then do let us know, see how we can help you. And one small difference I will do today is I will do a pace check in between the class. So I'll ask you guys, how's the pace so far? Do you need me to speed up? Do you need me to slow down? So it kind of gives me a better connection, how the lesson is like for you guys. Okay. All right. Now, just to maybe kick off today's lesson, what I would like to do is I'd like to do a recall of the important things that we did last week. Some of the feedbacks we gathered was that the portion on SPDF is very new to you guys, right? So especially the JAE students who have not really heard of SPDF, is somewhat confusing at certain parts. I acknowledge that, right? So what I will do is I will do a very elaborate but quick recall with you guys, okay? So all this are recall. So what I'm going to do is I'm going to go into a share screen right now. I will use a blank canvas to walk through this with you guys, okay? So as I use my blank canvas, I do encourage you to also have a piece of paper. If you have a data booklet or periodic table, can you go get it as well, right? A data booklet or periodic table, it'll be useful for today's lesson. Okay, right? So you can see my screen right now. I'm just going to share a little bit of stuff. Okay, I'm just going to use a blank canvas to explain the idea of the SPDF notation, what is a quantum shell, what is a subshell, and what is an orbital. Okay, so I'll begin drawing this way. You know, at O levels, we have learned this thing called the nucleus, right? And outside the nucleus, you have different shells. So at A level, shells are called quantum shells. Right? The very first shell we have is called n is equals to 1 quantum shell. Then the second shell is n is equals to 2 quantum shell, so on and so forth. Then we have n is equals to 3, and then we have n is equals to 4. So I think most students are perfectly fine with the concept of quantum shell. Now, the problem is what happens when you go deeper into a shell? So imagine you have a microscope, right? And then you keep expanding and you keep expanding. What do you see inside a particular quantum shell? There'll be this thing called subshell, right? So subshell is simply just a division, right? A division of the quantum shell. So subshells comes in different categories, right? There will be what we call the S subshell. There will be the P, the D, and the F. Okay, so what you must know is if you are in the first quantum shell, you have one subdivision, right? So there will be what we call the 1s subshell. If you're in the second quantum shell, then you will have what we call the 2s as well as the 2p. There are two subdivisions, right? And if you're in the third quantum shell, there will be three subdivisions. There will be the 3s, 3p, and the 3d. And then if you're in the fourth shell, you will have what we call the 4s, 4p, 4d, and 4f. Right? So just remember, depending on which quantum shell you are in, the number of subdivision or the subshell will correspond to the quantum number. That means if you're n equals to 1, you have one subdivision. If you're n is equals to 3, you have 3 subdivision, so on and so forth. All right. Now, if you go deeper into a subshell can be further subdivided into this thing called orbitals. All right. So if you look through your notes, we have explained to you guys that P subshell is categorized further into 3 types of orbitals. We have what we call the 2px orbital, we have the 2py, and we have the 2pz orbital. Right. The S, there's only one orbital, so we'll call this the 2s orbital. Now, the difference between the S and the P orbital is generally the shape. Whenever we have an S orbital is round and spherical, right? When it's the P orbital, now P orbital is going to be dumbbell shaped, right? And when they are dumbbell shaped, they will go along different axes. So you have your x-axis, y-axis, and z-axis. So a few students were a little bit confused about the way that we draw the axis. Now, the way you draw axis is very three-dimensional, right? So conventionally, when we do mathematics, we always say this is y and this is x, okay? So if your orbital moves along the x-axis, we'll call this the px orbital. And likewise, if your orbital moves along the y-axis, we'll call this the py. But because your x, y, z axis is three-dimensional, now it is also perfectly fine if we label this as the z-axis this way, right? And then you have an orbital that moves along the z-axis, we'll call this pz. So conventionally, we will say x is here, y is here, z is in and out of the plane. Conventionally, it's like that, right? But you must be aware, the way that you label is very flexible, right? You can call this the x-axis, you can call this the z-axis. So in exams, how do we mark your script? It's very simple. We will look at how you label this. And whatever axis you're pointing towards will represent the kind of orbital. Along the x-axis will be px, along the z-axis will be pz. Okay, so this is the subdivision for the P subshell. Now, the D subshell is even more complicated because the D subshell are further broken down into 5 different types. So if you take a quick look at your notes, what are the 5 different types? Now, you are expected to remember them, right? The 5. Okay, I run through with you a very quick revision. So you have, first of all, the dxy. Okay, what else do we have? We have the dxz. And then the last one is we have the dyz. So how to remember this is simply a permutation of your x, y, z. We just put 2 of them together, right? That becomes the way that you label the 3D orbitals. And there are 2 of them that has some sort of power to it. So for example, one of them will be called the dx squared minus y squared. And then the last one will be the dz squared, right? So what is the general shape that the d orbitals will have? We have a name for it. We call this the clover leaf shape. And clover leaf will just be 2p orbitals that's combined together. The only exception you have is the 3dz, right? The 3dz will look like this. You have your z orbital, then you will go 1p orbital over it, and then the second one is like a ribbon or a loop that goes around the z-axis as well. Okay, so this will be the subdivision. When it comes to F, now F, there are 7 types of orbitals. You don't need to know how to draw them, how to label, even I can't do it as well. Okay, so if I consolidate for you nicely, right? We were using the building, the classroom analogy. Okay, I'm just going to consolidate one last time before we move on together. So you can imagine, right, that an atom is like a building, right? A building has different levels, just like an atom has different shells. So the first level that you're looking at is n is equals to 1, or the first quantum shell. So in the first quantum shell, there's only one subdivision, one subshell, and subshell will be the classroom. So there's only one classroom, and the only one classroom will be defined as the 1s classroom. Okay, then if you look at the second level, that means n is equals to 2, there are 2 subdivisions or 2 classrooms. So the 2 classrooms will be your 2s followed by the 2p. Okay, then if you look at the third one, you will have 3 classrooms. There will be the 3s, there will be the 3p, and there will be the 3d. And finally, you have the 4th level. Then the 4th level will have your 4s, 4p, 4d, and 4f. Okay, so this is the subdivision that we have inside an atom. But you must know, the moment you walk into a classroom, you are going to see tables inside the classroom. The tables is a further subdivision of the classroom, and therefore the tables are the orbitals, right? So when you go into the S classroom, you will only see one orbital inside the S classroom. When you go into the P classroom, it doesn't matter which level, whether it's level 2, level 3, or level 4. So long as you walk into the P classroom, you will always see 3 tables. All right. So here, 3 tables will represent 3 orbitals. And likewise, if you move into the D classrooms, you're going to see 5 tables, and there'll be 5 orbitals. And finally, your F classroom, there'll be 7 tables, and hence 7 orbitals. Okay, now do remember, every orbital can seat, every table rather can seat 2 students. All right, so what it means is inside every orbital, there are 2 electrons that's inside. So if you look at the breakdown, right, inside your S, there can only be 2 electrons. All right, so here there are 2 electrons, 2 electrons, and 2 electrons. But P, because there are 3 orbitals, it will be able to seat 6 electrons or 6 students, right? So you can imagine there will be 6 here, there will be 6 here, and there will be 6 here. And then for the D, because there are 5 tables and every table can seat 2 students, you'll be expecting 10 electrons or 10 students. And finally, for the F, there will be 14 electrons. So when you begin to couple everything together, you will more or less understand this theory, why the first quantum shell has a maximum of 2 electrons, why the second quantum shell has a maximum of 8 electrons, the third quantum shell has a maximum of 18 electrons, And the fourth quantum shell, if you calculate everything and you add it up nicely, you will notice they can fill up to 32 electrons in the fourth quantum shell. Okay, so this is the entire breakdown of how your electrons are going to work. What is a quantum shell, a subshell, orbitals, and electrons, so on and so forth. All right, so this recap and recall is hopefully to give you a nice consolidation, whatever things that we have done previously. Okay, now let me just look at the chat. All right, okay, so I just want to do a poll with you guys real quick, right? I just want to make sure that you guys are comfortable. You kind of understood the SPDF. If it is yes, you let me know. More or less there, let me know. If you are still very unsure, also let me know. Okay, good. I can see that most of you guys are relatively clear or more or less there. Okay, thank you for that. Okay, so you can see, right, most of you guys are relatively clear. So if you still have small doubts here and there, maybe after class or during the consultation or Telegram, send us a chat. Let us clarify those little questions with you guys. Okay, all right, excellent. Okay, so once you're okay with this, what I'm going to do next is I'm going to invite you to flip back to your notes or your encyclopedia. Can you turn to page 116? No, this page, right, which is on the rules for determining the ground state. Okay, can you flip to this page, which is on page 120? Okay, 120. Okay, so after you have understood how electrons are being distributed, the next thing is to know the sequence of filling up, right? So some students in class, they ask, okay, I kind of got what you're trying to say here, but what is this thing? I mean, how is this thing being derived? They have this question, right? You don't need to know how this thing is being derived. It's just a technique, right? What this technique does is it gives you a way to easily know the sequence. That means whenever you have electrons, the very first orbital you must fill up will be the 1s, right? The second must be the 2s. It is simply giving you a sequence of filling up. All the intricate details is really not important for you, right? Just be mindful there's one exception we mentioned last week, is that the 4s actually comes before the 3d, right? So when you write your sequence of filling up electrons, we always will say 1s is the first, 2s, then 2p, 3s, 3p. Now, you don't do 3d, right? You do 4s followed by 3d. So this is the so-called anomaly or the exception, right? Why is it like that? I'll explain later, but you must accept this is the sequence of filling up of electrons, okay? Now, we also mentioned to you guys, because every orbital can hold 2 electrons, so the 2 electrons must be having opposite spins. If not, they're going to repel each other, right? So you can see how we represent the opposite spin is you show one of them going up and one of them going down. You cannot show them in the same direction because they're going to repel each other. That is rule number 2. All right. Now, rule number 3 is in an event, you have orbitals that has the same energy level. Okay. And this is where a few students got a bit confused. All right. So let's say you have the 2s and the 2p. All right. Now, 2s has only one orbital, but 2p, there are 3 orbitals over there. So you must accept that 2s is always going to be filled up first. Only after 2s is filled up, then you'll be filling up the 2p. So when I fill up the 2s, I will go first guy like that. Second guy, I cannot go into the 2p yet because I must finish filling up the 2s, then I'll move to the 2p. But when it comes to the p orbital, because you have 3 of them that has the same energy level, you can consider splitting the electrons up whenever you can. So the first guy will go into one of the orbitals here. The second, they will not pair up, right? Because of social distancing, remember, right? And then the third one, they will also not pair up. Only when it comes to the fourth guy, they will begin to consider pairing, right? Because all the tables have been filled up, they will begin to pair up, then the fifth one, and then the sixth one. So be very comfortable, right? Hund's rule is talking about orbitals that has the same energy level. So it works for the p orbitals. It also works for the d orbitals, right? Because the d orbitals, there are 5 of them that has the same energy level. So when we begin to fill up electrons, it will also be singly filled before they begin to pair. Okay? All right. Now, once you're okay with this, okay, now I'm going to go through your homework questions on page 121. Okay, let's take a quick flip to the next page. Okay, now on page 121, you're required to look at all this configuration and you begin to fill up. Okay, so as we have mentioned to you last week, right? The first thing is to know the sequence. So the sequence will go like that: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. All right. So it's about, if you have a certain number of electrons, you must always make sure this is full before you can go to the next one. Make sure it's full before you can go into the next one. All right. So I think we have done carbon with you guys, right? Mr. Yap, he has already done the portion on carbon, so I won't be explaining this again. So you can see, right, carbon, there are 6 electrons. So how will the 6 electrons be distributed? They will be distributed this way. Okay, what I do want to touch on is vanadium, right? So when you look at vanadium and you notice that there are 23 electrons, right? Just remember this, there are 23 electrons. How will the 23 be filled up? You must make sure 2 of them will enter the 1s. The next 2 will enter the 2s. So at this moment, can you see that 4 electrons have been filled up? You need to continue this sequence until you fill up all 23 electrons. All right. So I'm going to show you the notation first. Okay. The easy parts, right, will be here. Okay. We slow down a little bit. Now, to go from 1s2 to 3p6, this will be how your first 18 electrons are going to fill up. Okay. So you can count, there are here 10 electrons, and then here there are 8 more electrons. So the first 18 electrons are going to be distributed this way. Now the question is, after filling up 18, I have 5 more electrons. Where are the 5 electrons going to go? All right. So you must accept all this are fill up. The next person that comes should have been the 4s, right? So I'll be expecting 2 electrons to go into the 4s, and after which I will have 3 remainder electrons that will then go into the 3D subshell. Okay, but you notice the way that we present is very strange. We didn't write the 4s before the 3D. We write it as the 3D before the 4s. Now, there's a reason for this, okay? I'll come back to this in a short while, but I need you guys to flip all the way down, okay? Can you go all the way down, right? And you see there's a portion over here. Now, can you put an asterisk on this, okay? Super duper important. Now, it says over here, when the 3D subshell is unfilled, the 4s orbitals are lower than energy, but the moment the 3D subshell is occupied, there will be some electronic repulsion that causes the 4s electrons to have higher energy. Okay, what it means is this, okay? Now, I need you to take a look. Below, these are empty orbitals. That means electrons have not filled up the orbitals yet. They are completely empty of electrons. According to the rule that we learned just now, 4s is lower in energy because it's closer to the nucleus. 3D is higher in energy. So 4s becomes the inner subshell, and then 3D becomes the outer subshell. But imagine, right, as electrons begin to fill up, right? Let's say I have an electron going here into the 4s, the second going into the 4s. Now, after which, they'll begin to fill up the 3D orbitals. Now, the thing is, right, the 4s and the 3D orbitals, they are actually very, very close in energy. They're almost touching each other, right? And the moment you start filling electrons into the 3D orbitals, there will be some sort of electronic repulsion. Okay, so I use a different color to explain that the 2 subshells begin to repel each other. So when they begin to repel each other, the repulsion is going to result in, look at my color code, the 4s going from the inside to then the 4s going to the outside, right? So I'm going to label, now the 4s becomes the outer subshell, but the 3D becomes the inner subshell. So this is true every time electrons are filling up the orbitals. Can you see here? This is for filled orbitals, okay? Filled orbitals. And when you do your question, okay, let's go up, you understand this? Okay, let's go up. What we are writing right now is orbitals that has already been filled. So for orbitals that has already been filled, you need to be very careful that now the 4s is going to be the outer subshell, not the inner subshell. So it's something that they expect you to do it on your own. They expect you to understand that the 3d and the 4s are going to swap position, right, after the electrons are being filled up. Okay, all right. So with this idea in mind, okay, let me just clean up a little bit. Okay, let's delete this. Right, so this is what happens. We have already drawn the electron in a box for you, right? So the first few, these are very straightforward. Just be mindful, the 4s will be filled up. Then the 3d, make sure they are singly filled. Do not pair them together, okay? All right, now let's move to the next one. All right, the next one is F minus. Now, to look at F minus, what you should have done is you should have done fluorine first, right? Fluorine, there are 9 electrons. So if there are 9 electrons, the distribution will go this way. 1s2, 2s2, already 4 electrons. I have 5 more electrons. I need to go into 2p5 to fill up the 9 electrons. Okay, but be very mindful, this is a F minus. So when you're F minus, it will mean that you are going to gain 1 additional electron. So the additional electron must have been going into the 2p orbital since there's space for 1 more electron. Therefore, the overall answer is going to look something like this. It will be a 2p6 instead of a 2p5. Okay, so you use this and then you just draw the electron in the box. Okay, this one is quite straightforward. So you end up with this answer, 1s2, 2s2, and 2p6. Okay. All right, now the complicated one is actually Fe3+. Okay, this one you really must be very, very careful. As we ended the class last week, now Mr. Yap explained to you guys that you should be writing the non-ionic version first. Okay, the non-ionic version. Okay, that means you should be writing iron first, right? If iron has 26 electrons, how will the 26 electrons be distributed? Okay, we run through together. You will have 1s2, 2s2, 2p6. Okay, so you can see as of now, I have 10 electrons that's already filled up. After which you have your 3s2, 3p6. Okay, there's going to be 8 more electrons that's filled up. Okay, then what happens? You must be filling up the 4s2 first. So if you count the total number of electrons, you will notice right now, there are already 20 electrons that has been filled up. The remaining 6 of them must have gone into the 3d orbital. So you will end up with a 3d6 that represents the remainder of the 6 electrons. Okay, but remember, this way of presentation is not correct, right? What you should do is you should push this to the outside, right? Remember, you have to push the 4s to the outside. So if I were to clean this up and I write it this way, it should have been 4s2 on the outside and 3d6 on the inside. Now, you begin by writing this way. And then you begin to realize I am removing 3 electrons. Okay, so if I were to remove electrons, it would be most logical for me to remove electrons from the outermost subshell, right? So I should be removing electrons from the 4s. So you can imagine, right? I'm going to take 2 of them away. And then the last one, which I'm going to remove, is going to come from the 3D subshell. So this is why the final answer towards that question is like that, a 3D5. And if I be a bit more accurate, it's a 4S0. All right. If you do not do the switch, you will probably be mistaken, thinking that I will take everything away from the 3D and I will leave the 4S, because you kind of forgot that the 4S is going to go to the outside, right? So the 4S should be the first electrons to be removed. Okay, so always have this idea. In order to work with cations, you start by writing the non-ionic version. Okay, write it down. Start by writing the non-ionic version. then you remove electrons accordingly. It will be a better way for you to solve for the answer. Okay, let me just push this up. Then I'll clean this. And you can see this is how it's done. We'll end up with a 3D5 by the end of the reaction. Okay, so these are fundamentals, right? So it's important you get this correct because once it's done, right, everybody, myself, your school will assume that you kind of know this thing very well and they'll just zoom past this. The initial learning curve is a bit steep, but once you get it, right, everything will fall into place for you. Okay, all right, now let's move on to the next page, shall we? I'm going to touch on this thing, which is called exception. Okay, whatever things you learn generally hold, but there are two exceptions. Okay, I need you to ask you, is this super duper important? Now you notice that there are two guys, chromium and copper, they do not follow the usual way of writing. Okay, for example, if someone has 24 electrons, you use whatever rules we mentioned just now, right? You should not have this because we always say you should fill up the 4s. Make sure the 4s is full before you then go on to the 3d. So if you write it the by right way, or I can call this the expected way, according to what we have learned, you will end up with a 4s2 and a 3d4. And likewise, for copper, which has 29 electrons, if you go and write the configuration, the expected should have been a 4s2 as well as a 3d9. Now, we kind of expect this, but these guys are exception. They do not follow what we expect. There's a reason for this. Okay, you see here, if I am 3d4 and 3d9, okay, bear in mind, d orbitals can have a maximum of 10 electrons, a maximum of 10, right? So when you're d4, right, d5 is very, very close by. If it's D5, D5 is called half-filled subshell, right? If it's D10, then D10 is called fully filled subshell. So the main understanding that you must get is this. Whenever you have something that's half or full, right? Half or full is always going to be more stable. So in the case of chromium, listen, chromium, realize that you are 4s2 and 3d4. I'm 3d4. I am so close to a d5. So what will they do? They will do a mini adjustment, right? They will adjust. And how will they adjust? Is they will ask the 4s, 3d will ask the 4s, hey bro, I'm very close to d5. Can you help me by giving me one of your electrons? And 4s being the nice guy will say, okay, I'm going to give you one electron. So the transfer will happen from the 4s to the 3d, and the end result is 4s then becomes a 4s1, and 3d becomes 3d5. So that 3d becomes stable. So 4s is very willing to sacrifice himself so long as 3d becomes happy. All right? It's the same idea here. 3d9 is super close to d10. So he will ask, bro, can help? And he says, no problem, I'm going to give you one electron. So the end result is your D now becomes D10 and is more stable. Okay, so very often in class, right, students will ask, okay, I kind of get what you're saying. If D4 can become D5, can I extrapolate that D3 will ask 4s to give him 2 electrons? The answer is no. Right? It must be very close. So the only time this thing happens is when you're D4 or D9. That's why the only exception we have is chromium and copper. So bear in mind, these guys are very unique. They're very different. All right. And you can see the reason why half of fully filled subshell is stable is because less energy is needed to maintain an electron in a half-filled or fully filled subshell. Okay. Now, something else that you may want to take note, I'm going to clean this up. Okay, how come 3D and 4s can easily interchange electrons? What is the reason for that? Okay, I need you to take care of this. Let me just clean this up. Now, the reason is because the 3D and the 4s orbitals are very close in energy. All right, they are very, very close. So it's very easy for the electrons to jump from one orbital to the other. Okay, I can show you a picture to like consolidate this. Okay, let me find a picture. Let me see here. You go back a few pages. Yeah, can you go to this page? Page 119. Everybody, can you flip with me? You go to page 119. All right. Now you notice, right? All the 1s and 2s, can you see that the energy gap between them is like very, very big? All right. Then 2s and 2p, the energy gap is also fairly big. But then the 4s and the 3d, now this thing is not drawn to scale. But the reality is that the 4s and 3d is so close in energy. They are like almost touching each other. The 4s is just marginally lower than the 3d, right? So that is why for them, it's okay to interchange the electrons so long as the 3d orbitals become more stable than before. Okay, this is how it works. Okay, good. Now let's move on. Okay, something that's probably quite new to you guys. There's this configuration. Instead of writing the SPDF, we'll use this thing called the noble gas configuration. Now, the noble gas configuration is almost like a shortcut, right? You can see all the way down, you look at the table. Sometimes it's just very troublesome. Can you imagine, right? We have this guy, 45 electrons. And how long are you going to take to fill this up? It's going to take a long time, right? And we don't like this. So we have created a shortcut to simplify this with a noble gas in front of it. Can you see the square bracket of the noble gas? So all these are shortcut for you to cut down on the way that you write electronic configuration. Now, to master noble gas configuration, I need you to take out your periodic table or your data booklet. Okay, can you take that out right now? I'm going to run through with you how it works. I need you to flip to the periodic table. Okay, if you don't have a data booklet, the substitute will be what is inside your notes. But if you have a periodic table, I truly recommend you use a periodic table, which is what I'm going to do right now. Okay, now if you look at the periodic table is broken down into actually different blocks. Now on the left-hand side, this is called the S block. Okay, so the S block will be the first two groups of your periodic table. This is the S block. Okay, then you have the P block. Now, the P block will be from group 13 all the way to group 18. Now, please take note, at A level, we don't call it group 3, group 4. The names will change. It's group 13 all the way to group 18. Those are called the P block. All right. Now, those in the middle, okay, those in the middle. So I'm going to shade this. Now, this is called the D block. All right, the D block. And all the way down, right, the two you see here, lanthanides and actinides, they are what we call the F block elements. So your SPDF is actually distributed this way. If I further break down the different blocks, okay, write this with me. This is called S1, S2, okay? Then this is called P1, P2, and if you continue writing all the way to P6, for the D block, it will be written this way. D1, D2, D3. Okay, we don't write all, right? We just go all the way here to D10. Then for the F, okay, it will be like that. F1, F2. If you continue writing all the way, it will end with F14. Okay, let's dissect the periodic table further. Everyone, you should know this represents the first period of the periodic table. So we will label this as n is equals to 1, right? That means the first period of the periodic table. Okay, then I use a different color. Can you see? What I'm doing now is I'm shading the second period. So I'm going to call this n is equals to 2, and so on, right? Then this is n is equals to 3, n is equals to 4, and n is equals to 5. Now, earlier on, you have learned how to write the full notation, but now I can teach you a shortcut that's very, very powerful. Okay, for example, okay, look at this. If I need to know the last orbital of selenium, look at selenium, right? I can tell you with precision, right, where selenium will be because selenium is in period 4 and selenium is P4. So if you write the configuration for selenium, you go like 1s2, 2s2, you skip the middle, I can guarantee you, you will finish with a 4p4. So this is your n equals to 4, this is your p4, right? It's almost like you play those treasure hunts. There'll be grids on the box. This is A1, A2. You're trying to match the exact position of that particular species. Okay, so I just try one more with you. Okay, let's say we have silicon. All right, what is going to be the last orbital of silicon? You can see that silicon falls into 3 and then it will end with a P2. So I know with certainty silicon, when I write the configuration, 1s2, 2s2, blah, 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 it must finish with a 3p2. All right, that is the shortcut for me to know the last orbital. And it's super important because when you do chemical bonding, the valence orbital is what takes part in chemical bonding. Okay? Okay, so why am I telling you this? Right? Because let's go back to our, let's say, silicon example. Okay, follow me up. Now I'm on silicon. Now, if I want to know what is the noble gas configuration of silicon, what I should do is I need to work backwards. Okay, you look at silicon. Silicon is number 14. You work backwards. There's 13, there's 12, there's 11, there's 10. You look for the last noble gas. Okay, the last noble gas. So if I have silicon, the last noble gas will be neon. All right. When you write a square bracket neon, it is a shortcut to represent all the electrons that neon has. The first 10, you don't have to write anymore. It's all already inside the bracket. Okay, but you must know you have only covered the first 10 electrons. You must tell me what happens to the 11th electron, the 12th electron, the 13th, and the 14th electron. So how do we do that? Is you use the mapping. All right, so you can see this is in period 3. So to account for the 11th and the 12th electron, it must be occupying the 3s2. Okay, you can see this one is 3s1. This one is 3s2. Okay, next, my 13th electron is going into the p orbital, and I have to account all the way until 14 electrons. So this guy will end off with a 3p2. So this becomes the noble gas configuration of silicon. Okay, now I'm going to show you one more. Okay, let me just clean up a little bit. Okay, let's clean up. If you're not very sure, it's okay. I'll show you one more, right? The next one should be a lot easier for you. Okay, let's say I have maybe, let's see, something a little bit harder. Okay, let's have bromine. Okay, bromine. Now, bromine, there are 35 electrons. Okay, so what is the rule? You work backwards and you look for the last noble gas that bromine has. What is the last noble gas? Can you see the last noble gas is argon? All right, so we'll do a square bracket with an AR. So that would have covered the first 18 electrons. But after that, you must tell me where the other electrons will be, all the way until you have 35. Okay, so this is where you do it bit by bit. You first account for these two guys. Now, these two guys is going to be inside the 4s. Okay, the 4s. Okay, the next one here, I'm going to shade this in blue. Is it called the 4d10? Is it called the 4d10? The answer is no, it's not the 4D. Okay, because remember, when you write configuration, 3D comes before the 4S. Then after that, you have the 4P, sorry, the other way around. The 4S comes before the 3D. Then you move back to the 4P. So what I'm trying to tell you is this, okay? This is called the 2S block, 3S block, 4S block, but this is not the 4D block. This is the 3D block. So for the D species, they do not correspond to the number here. If the number is 4, this guy is actually 3D. All right. Now, let me show you one more just to be sure. For this guy, okay, the one I'm boxing up in pink right now, although it is in n is equals to 5, but he's actually what we call the 4D block. So D doesn't follow the number. D, you have to minus 1 away, right? Because 4s will come before 3D. The moment you go into D, the number will drop by 1. Okay? Now, anyway, coming back to where I have, okay, I was on bromine, all right? So after bromine, you have your 4s2, okay? Then the next one, you have to account for all the electrons over here, and these electrons will represent 3d10, okay? 3d10, followed by electrons 31 to 35. So electrons 31 to 35 will now be my 4p5. And that's why this is the noble gas configuration for bromine. But a small mistake, okay, what is the mistake? Is you must always put your 4s outside. Remember that once it's filled up, right, the 4s is always going to go to the outside. Okay, so that will be the noble gas configuration. Okay, just to consolidate and make sure that everybody, you are okay, you understand with what's happening, you return back to the examples that's given. All right, so now you try to connect. Okay, let's use one example, maybe. Okay, let's use perhaps iron. Okay, iron has 26 electrons. So what do we do first? You locate where is iron inside your data booklet. Okay, so I'll do this a lot faster now. Okay, let's clean up. Okay, where is iron? Iron is here. So what do? I look for the last noble gas. The last noble gas is argon. So to write iron's configuration, I have a square bracket AR, which covers the first 18 electrons. Then after that, I have to mention what happens to electrons from 19 to 26. So I will do it bit by bit. I have here the 4s2 electrons. And then this portion will be your 3D, 1, 2, 3, 4, 5, 6, 3D6. Okay, but remember, push the 4s to the outside. And that's why the answer that's given to you, you can see from your notes, right? It will be a 3D6 followed by a 4s2. Okay, as I say, I can have a feedback because I don't see you in class, okay? But I think I've tried my best to explain to you. Okay, why don't you do this first? I have a few questions for you to try. All right, can you quickly walk through the example here? Try to write a noble gas configuration, and then I'm going to bring out a poll. Once you're ready, you just click and let me know that you're done with the poll question. Then I'll share the results. Okay, let's begin. Okay, about 70% of you guys are done. Okay, I'm just going to end the poll, right? And then I'll just show you those that are quite straightforward. One or two, most likely you will make a mistake. Okay, I'm going to end poll right now. Okay, the first one, AL should be like that. The last noble gas is neon, right? So neon will have covered the first 10 electrons. Then the next three will be in the 3s2 and the 3p1. Now the next one, titanium. Titanium should be using the noble gas core of argon. So argon will have taken care of the first 18 electrons. Then the next four will be your D2 and 3D2 and 4s2. So please take note of your presentation. Make sure that your 4s is on the outside. Common mistake that people will make. Okay, bromine, I think I've already explained just now. This is how bromine works. Okay, the one that you may get confused, remember, right? Silver is an exception. All right, why? Because if you have written 4D9 and 5s2, the D9 is very close to a fully filled subshell. So he will ask the 5s, can you bring one electron over? And 5s will help the 4D. So it is the same idea as your 4s and 3D. Okay, now that it's being extrapolated to the next guy, it really doesn't matter which quantum shell they are in. So long as it's D and S, they will always have the ability to interchange electrons with each other. Okay. All right. Now for iodine, this one I think is pretty straightforward. This will be how we write the configuration. Okay, leave this here for another 10 seconds, just to make sure everybody are okay. Then we'll move on in about 10 seconds. Okay, good. Now let's move on. Okay, we're going to do something brand new right now, something that you probably haven't learned before. Now, it's a concept called ionization energy. Okay, what I need you to do is, if you have, again, your data booklet. Now, can you just flip through your data booklet, right? There'll be certain portions on ionization energy. Okay, I'm going to find my data booklet. You try to find your data booklet. Okay, so this was a data booklet. Let's skip. Okay, then you will see this portion, right, that says ionization energy. So ionization energy comes in different forms. We have the first ionization energy, the second, the third, as well as the fourth. Now, I need you to take a good look, and you notice that there's a trend across all the ionization energy. Okay, I've spoken a lot already, so now it's time for someone to speak. Okay, Tipin, I can see you. Hello, Tipin. Hi. Okay, don't wave, speak with me. All right, Tipin, can you tell us, you look across first, second, third, and fourth. What is the general trend you see across the entire table? Can you tell us like the values? Does it get higher? Does it get smaller?
Values are all very uneven.
Can you see that, for example, from here to here, here to here, it's quite clear that the values always are increasing. Can you guys see that? All right, so that is the trend for ionization energy. Maybe write it down somewhere. Successive IE always increases. Okay, this is a fact when we're doing ionization energy. Why is it like that? I'll explain to you in a short while. Okay, all right, now at least you know where to find this in your data booklet, because you may need this to do calculations, or sometimes you may even need this to plot graph. Okay, so let's go into back to your encyclopedia or back to your notes. Okay, I'm going to change right now. Okay, now to understand ionization energy, I'm going to draw a very simple picture for you. Okay, so imagine we have here, this is the nucleus, and you have electrons that's around the nucleus. What is the job of the nucleus or the proton is to basically suck the electrons in. And in chemical bonding, right, those who came for class this week, we explained to you any attraction between plus and minus is known as electrostatic attraction. So you must be mindful that the protons and the electrons are electrostatically attracted. That's why they are within the atom itself. And what we do in ionization energy is to actually remove that electron. So how do I remove the electron? I need to break away the bond, right? So you must be mindful. In order to remove the electron, you need to break the bond. Then this electron can be removed. And that is the concept of ionization energy, right? That's why you can see the definition. You must know the definition, okay? Non-negotiable. They will ask you straight in the face, define first IE, define second IE. So first IE means the energy that's needed to remove 1 mole of electrons from 1 mole of gaseous atom to form 1 mole of gaseous cation. I wouldn't really hardcore memorize it, right? I'll take note of the important things. You can see from the picture, it's very easy to understand. This guy must be gaseous. So an example here, this is X that's going to be gaseous. And I'm just telling myself, what is happening here is I am removing the first electron. Okay, I'm removing the first electron. So once I remove the first electron, this guy becomes X plus gaseous, and there'll be electrons floating around. And if you know your basics, this is a bond breaking process. Bond breaking process is always an endothermic process. That's why it's a positive value, not a negative value. All right. Now, to build on this, after you remove the first electron, you can remove the second electron, which is called second ionization energy. All right, so I don't need to memorize this, but I can see the first electron has already been removed. So what is happening now is I'm going to remove the second electron. So when I remove the second electron, now this guy becomes X2 plus as well as electron floating around. Okay, so you notice subsequent IE, whether it's the third or the fourth, we're going to define them in a similar fashion. And delta H is an endo, because you take in energy to overcome or to break the electrostatic attraction between the electrons as well as the nucleus. And also bear in mind, if you have many, many electrons, okay, for example, if you have the nucleus, right, there's like the first shell, the second shell, the third shell. When you do IE, it is very logical you are going to remove the outermost electrons because the outermost electrons are the least strongly attracted to the nucleus. It must have been the easiest to remove. All right, so be mindful here. Electrons from the valence shell are the least strongly attracted, and therefore is always going to be the first to be removed. Okay, so this is the concept. Now let's look at different types of questions that IE will bring. Okay, let's move to the next page. Okay, you must be able to interpret. It is not negotiable. Okay, super important concept here. I'm going to give you a question that says, this is the successive ionization energy of sodium who has this configuration 1s2 all the way to 3s1. Okay, so as you begin to consolidate whatever we have learned, you will understand this is your first quantum shell, n is equals to 1. All right, then this portion here is your second quantum shell, n is equals to 2, and then you have your third quantum shell where n is equals to 3. So remember, which electrons are going to be removed first is always from the outermost shell. Okay, so I'm going to write here, these electrons, the 3s, are going to be removed first. After you finish removing this, you will then go into the second quantum shell. So this is going to be removed the second. Then finally, this will be removed the last. So you notice one thing, right? As this graph is showing, okay, this is a new graph, but the axis here is ionization energy against the number of electrons removed. So what it means is, this is the first electron being removed, the second, the third, right? So up to all the electrons over here, you're just removing them in sequential order. Okay, then remember, just now we were discussing with T-Pin that the trend is IE is always going to go up, right? Successive IE increases. But the strange thing is, you don't always have a linear increase. Now, there will be portions where it's an exponential increase. Can you see that? I'm highlighting them in green, right? So it's always increasing, but to different extents. Okay, how do we explain this? All right, so if you take a look, the first electron, remember, is from the 3s1. Because this guy is in the outermost quantum shell, it must be the super easy to remove electron. Okay, so I use layman's term. This is very easy to remove. I need very little energy to remove it. That's why this guy comparatively has the lowest ionization energy. Okay, but imagine this. If I were to draw the shells, okay, you see here, the first shell, maximum 2 electrons. The second shell, maximum 8 electrons. So we have 2, 4, 6, and 8. Then the third shell, you have 1. Okay, so what is happening now is I have removed the first electron. If I were to remove the second electron, what's happening? I will go into an inner quantum shell. Can you see that? It's going to be harder, definitely harder to remove the second electron. So that's why there is an exponential increase. So every time you see an exponential increase, what does that mean? It means that there is a change in the quantum shell. Quantum shell just means the shell. All right. So what is happening now is you're removing electrons from the second quantum shell. Okay, so this will be the next 8 electrons to be removed from n is equals to 2. And then yet again, there is another change in the quantum shell. Until this will be the last 2 electrons to be removed. Okay, so very often you're given graphs. You need to interpret the graph, or sometimes you may be even required to draw the graph. Okay, but one small thing, guys, you notice, right? Okay, listen to this very carefully. As you remove the n is equals to 2, the first electrons that go should be the 2p6. Okay, because the 2p is further from the nucleus than the 2s. So I should remove the 2p, then I jump into the 2s. So technically, you see here, this is the 2p electrons. Okay, then this is the 2s electron. So when you jump from the 2p to the 2s, make a note here, there should be some difference. Which means, depending on the axis, okay, sometimes you may get a graph that looks like that. Okay, let me just clean up. It's getting a bit messy. Okay, you see here, this will be the first one. The next 6, 1, 2, 3, 4, 5, 6. You may see a small jump, right? A small jump that goes like that. Then after that, another huge jump. So this is trying to show that there is some difference when you go from the 2s to the 2p. Okay, but why is it that in some axes, you actually you're not able to see that there's a jump? It's really because of math, right? Because here, there's a lock to it. It's math, right? So when you lock, sometimes the difference becomes compressed. You're not able to see. It's like a graph, sometimes there's a difference, but because you compress it so much, you're not able to see the difference. So at the back of your mind, you need to tell yourself, there should be some difference. Sometimes I can see, sometimes I cannot see. It depends on the question. It also depends on the axis. Okay, you got this? All right, now let's look at the explanation. Okay, so it says below, within an atom, successive IE is always going to increase, as we discussed just now. So more energy is needed to remove electrons. The reason is this, okay, go box this up, from the increasingly positive ions, which will attract electrons more strongly. Okay, looks like a lot of words over there. Okay, let me explain to you this way. Okay, you follow me. If you have X, all right, now if I'm going to do the first ionization energy, what happens is I have X plus gaseous. If I were to do the second ionization energy, I will have X2 plus gaseous, and so on, right? I will have X3 plus gaseous. Okay, you must bear in mind this. When you have electrons, electrons are attracted to the nucleus. So you compare the attraction that they have. Okay, you see here, I'm going to highlight this. This electron is bonded to a nucleus or a species that doesn't have a net charge, it's neutral. But now this electrons is bonded to someone that has a +1. So +1 will definitely attract the electrons more tightly together. Then later, when you do the second IE, +2 will have an even stronger attraction. That means the electrons must be even more difficult to remove. All right, and then you go on to +3, it's going to be even more difficult. So what I'm trying to point out here is because the charges keeps changing, and therefore it will affect the amount of attraction you have for the valence electrons. This is how we phrase it, increasingly positive ions that will attract electrons more strongly than before. Okay, so all the keywords must be there in your script. Okay, all right, so over here, everything we have mentioned, right, just put them in words and exams. Okay, then why is there a large jump from the first to second IE? I have explained. The reason is a change in the quantum shell. All right, so over here, because the second electron belongs to the inner quantum shell, there's only one valence electron, which is also meaning that this guy is in group 1. It has only one valence electrons to be removed. Okay, then also take note, there's a slight leap from the 7th to the 8th successive IE, which is here, this one, okay, the 7th to the 8th. There should be some small difference or small jump, right? Because you're moving from the 2p to the 2s subshell. And the 2s subshell has slightly lower energy as compared to the 2p. All right? Okay, now let's bring this into some questions to consolidate what we have learned so far. Okay, so there's a question here that says, I want to write an equation that represents the third IE of nitrogen, right? So if you're a bit not so fast, right, you can do it the longer way, which means, okay, first IE is you remove the first electron. Second IE is you remove the second electron. And the third IE is you remove the third electron. You can go through step by step, but there's a shortcut. Okay, can you guys see this? I use the one on top. Now, if you are doing, listen, if you are doing the second IE, you will finish with 2 plus. If you are doing the third IE, you will finish with 3 plus. All right? So over here, can you see that if I'm doing the third IE, the shortcut will be, I will finish with N3 plus. So to finish with N3 plus, what it means is my starting material should have been only a 2 plus, but what I do is I will remove one more electron from a 2 plus, then I will end up with a 3 plus, and there will be electrons that is formed. So this is the third IE of nitrogen. Okay, sometimes the question can get very tricky. Okay, let me ask you this question and see whether you can do or not. What if the question say, write an equation to represent the nth IE of nitrogen? Can you try? I'll give you 10 seconds. Write an equation, nth IE of nitrogen. Are you done? Okay, so what should be in your mind, right? To form the nth IE, you must end off with n plus, correct? Because third IE is 3 plus, second IE is 2 plus, so this guy must be n plus. And the number before this should be a smaller number, not a bigger number, okay? Should be a smaller number. So the correct answer will be nitrogen. This will be n minus 1 with a plus. Then you remove one more electron, it becomes n plus as well as electron. All right, so just remember the trick. Whatever IE, that will be the charge that they have, but the starting material is always going to have one numerical value smaller. From a 3, it becomes a 2. From an n, it becomes a n minus 1. Okay, all right, anyway, let's move back to the question. Okay, what is the max number of IE that nitrogen can have? You see, IE means you're trying to remove the electrons. So the maximum number of IE will also represent the maximum number of electrons that's found inside nitrogen, right? So if you look at your periodic table, nitrogen has 7 electrons. The max you can go is to remove all 7 electrons. So the answer very clearly is going to be 7. Okay. All right, now the last bit, this one is quite simple. The electronic configuration of nitrogen, this will be 1s2, 2s2, and 2p3, right? So altogether, the 7 electrons are distributed this way. Okay, good. Now let's move to the next question. Now in part D, okay, this is where it gets interesting. You need to draw a graph, okay, very common question. You need to draw a graph to show the successive IE of nitrogen. Okay, so what is the definitely will not go wrong way of drawing is you just write the configuration of nitrogen, right? On the previous page, we have done that. It will be the 1s2, the 2s2, and then the 2p3. Okay, let's get someone to help us again. Madesh, are you there, Madesh? Can you unmute yourself?
Yeah.
Hello, Madesh. Okay, great. Now, can you tell us, right, which are the electrons that will be removed first?
2p first.
2p first, right? So you have the first 3 that is easy to remove. Then, Madesh, still on you, will there be some sort of difference when we move from 2p to 2s?
Yeah, slight difference.
Very good, right? Yes, there's a difference, but it's a slight difference. Okay. Then when we move from 2s to 1s, there will be a huge difference. All right, a huge difference because you're changing quantum shell. You are not changing subshell, right? So the way that you draw, okay, I'm just going to build your thinking process. The way you think is very important. This graph is IE against the number of electrons that's removed. Okay, So your idea is, right, you are always going up because successive IE is always going up, but the extent of going up is not the same. All right. Through our discussion, right, Malesh have explained to us the first three will be easier to remove. Right. So how you draw it is you just draw, okay, this one is the first one, the second one, the third one. It must always be increasing, but it's increasing in a linear fashion. Only when you move to the fourth one, you're going into an inner subshell. So what you do is you show a small increase. It must be very clear. The gradient is different, right? So as you go up, this will be, let me label for you, removing from the 2p. Okay, then over here, this is removing from the 2s. After you have removed the 2s, you're jumping into the 1s, all right? So what you must show now is you must show a exponential increase. The difference between the two must be very clear to the person marking your script. All right, so in this case, what will happen is now you will be removing electrons from the 1s orbital. So as I repeat, right, draw this or write the configuration and rationalize to yourself which one is the first to be removed, which one is the second, whether there's a huge increase or a small increase. Okay. All right, now the next question. Ken, we're going to move on together. Okay, the next question is showing us the first 10 successive IEs of someone that is in period 3. Okay, so they will always tell us which period it is in. This is in period 3, right? So you can see this is the ionization energy against the number of electrons that's being removed. Okay, now let me arrow someone else. Wensing, are you there, Wensing? Hello, Wensing, are you there? Yes, okay. Can you tell us, right, okay, how many valence electrons do you think this species will have? Valence electrons means, you know, the one that's on the outermost, the one that's the easiest to remove. Okay, now can you see this one thing, right? You can see that this few are somewhat easy to remove. Okay, then this suddenly becomes a lot harder to remove. All right, so when you see like a small increase, probably it means a change in subshell. Right, and then if you see a huge increase, it probably means there is a change in quantum shell. So when I'm trying to interpret the question, okay, you got me, I see you nodding, thank you for that, right? So you will know that this must be within the same valence shell. They are the outermost electron. So you go and count how many electrons there are. There are 6 electrons on the outermost shell, all right? Then those here must belong to an inner quantum shell. Okay, but the trick is this, because the question already mentioned is period 3. So you just go to your data booklet or periodic table, check it out, period 3, which one has 6 valence electrons? The answer is sulfur. All right, this is how we interpret the question. Okay, so once you know it is sulfur, then it is quite easy for us to write the electronic configuration of sulfur. Okay, sulfur, if you go write it, it will look like that. 1s2, 2s2, 2p6, 3s2, and 3p4. So if you begin to connect, then you will notice this 4 must belong to the 3p subshell. This 2 must belong to the 3s subshell. So there is a slight increase because you are changing the subshell, okay, before you move on to a change in the quantum shell. So be mindful, right? This graph, it didn't show all the IE. It only showed the first 10. So there's more to it. It hasn't ended yet, right? So don't be confused by the graph itself. Okay. Now moving on to the next part. Why is there a huge increase from the 6th to the 7th IE? So you can see, right? This is the 6th and this is the 7th. The concept I've given to you guys is a change in the quantum shell. Okay, but how do we phrase it, right? Okay, you mentioned that when you remove electrons from the 6th, or rather you remove the 6th electron, this is remove, from the valence shell. The 7th is removed from an inner quantum shell. So when you remove things from an inner quantum shell, these electrons are more tightly held to the nucleus. So more energy is needed to remove this electron. Okay, right. If you're good, can you try question 3 on your own right now? Okay, I try not to give you clue first. You try question 3. I have a poll question. So once you're ready, you just click on the poll. Let me know your answer for that question. Okay, most of you guys are more or less there. Okay, I'm just going to show you the results, right? I think it's not too bad, I would say. Okay, let me share the results, right? Okay, so you can see a lot of you guys voted D, but a lot of you guys also chose A, B, and C. Okay, let's take a look, right? What is the fastest way to do the question, right? You may have your own thought process. I'm going to show you mine. So what we do is we look and we know that the IE is always increasing, but at different rates or different extent. So we always look for the biggest change, the biggest change. So you can see this is the biggest change. All right. So what it means is the first 4 must have been the valence electron, right? The 5th one becomes very difficult. The 5th one must have been in an inner quantum shell. So I will know that X must be someone that is group 14. There are 4 valence electrons, right? And the same logic, I can see that from the 6th to the 7th, there is a huge increase. So the first 6 must belong to a valence shell. So this guy is in group 16. Okay, some of you guys caught this, and then you were a little bit, like you took a bit of time to wonder whether it's ionic or it's covalent. Now, the best way to actually do this is to use something you're comfortable with. Okay, for example, what is something you know that's in group 14? Carbon, all right? What is something you know that is group 16? Oxygen. So how does carbon and oxygen combine together? Is there a species you know very well? Yes, CO2. And CO2 is covalent in nature, right? So that way of doing is a lot faster. Rather than you looking at a periodic table, really trying to figure out, match to something you're comfortable with. That's the best way to do questions like this. Okay? All right. Well, today is very content heavy. Okay, I still have a bit to go. I may end a little bit later. All right. Okay, I just wanted to just do a pace check for now. I've covered quite a fair bit of contents. Okay, just let me know, right? How's the pace so far, right? If it's okay, you want me to speed up, you want me to slow down, let me know. Okay, right. Thank you for voting. Okay, I'm going to share the results. So I think majority of you guys says it's okay. It's never going to be like 100%, right? It's always going to be like this. So a bit of you guys will think that we can speed up a little, and a small minority thinks we can slow down. So I'll try to reach a balance. Maybe I'll just like speed up a tiny bit, right? For the sake of the majority of the students. But remember, if you need more help, right, after class, when you come back to class, all this, we will help you. Okay, right. So thank you for that. It's useful so that I know how to continue from here later. Okay, now I have done a lot of talking, a lot of sharing. Okay, now I am just going to pass the time over. So, last week you had a senior, Shen Hui. She was sharing with you a little bit about how her GC life was like. If you remember what school she was in Dunman High. Now, today I have another senior who is going to share with you her GC journey, the struggles she has gone through, and some advice for you, right? So her name is actually Wei Ling. Wei Ling, she is from VJ, right? So she's in dance, a very good dancer. So right, I'm going to invite her out, right, to just share some of her experience and thoughts with you guys. All right. So I'm going to pass over to Wei Ling, right? So Wei Ling, I'm going to stop sharing. Okay, you will take over.
I can.
Okay, can you just take over?
Okay.
Yep, thank
You
you.
have to stop sharing first.
Okay, Ken.
Hi guys. Okay, so as Mr. William said, I'm Raylene and I'm from BJ. So I just graduated like last November and I'm still waiting for my results. So like next Tuesday. So yeah, so today I'm here to talk about my JC journey with all of you and hopefully give you some tips on how to survive JC. Yeah, so personally, I know all of you are from either IP or JE. Like from Sec 4 secondary school to JC, there's like a really huge jump in like the amount of content you have to learn, how in-depth the topic will be. So like the amount of content you have to learn in JC is like, I would say it's close to more than twice of the amount of content we learn in secondary school. But then the amount of time we have to learn is like half, like we only have 2 years, then secondary school is 4 years. So it's like learning twice the amount of content in half the amount of time. Technically it's like less than half because like we have to finish our syllabus like mid of J2, so it's like 1.5 years. So like of course there'll be some struggles. So I'm gonna share like some struggles I faced in JC1. So for chemistry in particular, I struggled with like 2 topics mainly. So the first one is chemical bonding. So I'm very sure chemical bonding is like the topic that you are going to learn soon. So this is just like a mini heads up on how this topic really kind of killed me lah. Yeah, so basically chemical bonding, unlike secondary school, is like, I would say there's much more content to memorize in terms of like the shapes of the molecules and their respective bond angles. Then you also have to draw like diagram drawing, like for example, hydrogen bonding. Then there's even like more types of intermolecular forces of attraction. So all these, like everything together, right, you have like much more content to memorize. So like I said, JC has a lot of in-depth content. So on the other hand, chemical bonding is more like content based, but for me, gaseous state, right, it was extremely tedious because it involved a lot of like calculations and like complicated formulas that you have to memorize. Then the calculations, right, you have to like have specific unit conversion, like you need a specific unit to get like the accurate answers. So all these, you have to like take everything into consideration, which makes it like super complicated when you do like a gaseous state question. So I think y'all will learn that soon. Yeah, so with that being said, I would like to emphasize like how important it is to like master your JC1 topics before you go to JC2. So like you have to master all the fundamental ideas because I would say in JC, based on experience, J1 topics and J2 topics are like super interconnected. Like everything can like overlap. So whatever you learn in J1 can also appear in J2. So if you don't like master the fundamental ideas you have in J1, it's very hard for you to catch up in J2 because of the amount of content that J2 will give you. Yeah, and I know some of y'all I had the mindset like, oh, I just want to promote. But I would say this kind of mindset is like very risky because like I said, J2 have so much content that if you only strive to promote, right, you will have like an accumulated amount of things you have to learn because like J1 you don't master your ideas, right? Then you bring over to J2. Then J2 you still have more content. So it's like a snowball effect. Like, so you keep adding on. Yeah, so it might create like a huge gap in J2 because you have to like catch up while other people is like starting to revise, then you have to catch up on like the amount of content you have because you are lacking in J1. So one tip is to constantly study in J1 because that will really give you a big help in J2. So scoring well in one exam is like one thing, but to consistently do well is like another thing lah. So one tip I like to share is that whenever you have questions, please ask your tutors because you do not want to like accumulate all your questions in one go and like ask them in like the end of the week or something. So like Making Sense, as you know, have like this Telegram platform where you can communicate directly to teachers. So you can just like spam them like as much questions as you want to clarify like any doubts you have. Or if you don't really like, you prefer face-to-face, then you have like mini consults after class. So like just ask questions that you face in class so that they can answer you on the spot. So you don't have to like bring home to us. Yeah, so the second tip, as you all know, JC is like very self-directed. So there's like lectures, tutorials. So it's very important for you all to like constantly keep up the lectures and also complete all your tutorials before class, because I'm sure you all do not want to go into class feeling like super aimless, like what's going on, like what's the teacher teaching about. And also for lectures, it's important to watch because the teachers won't give you time to watch during class itself, because class is just tutorials. So yes, must prepare beforehand. That's very, very important. And the last tip is very important to consolidate your learning. So for example, you have like 2 hours of tuition, like for example, in making sense. When you go home, you should spend like 2 hours to like consolidate what you have learned in that day, so that you don't really forget what content that has been entering your brain during the tuition. And also, Making Sense has this like Quizlet, small Quizlet platform where they will like give you like cue cards. Then it gives you small quizzes on like different topics. So I think it was really helpful for me because as like, for example, I go home, then on like MRT, I can just like take out my phone and look at the different quizzes to like help me remember what Mr. William had taught me during class. So like I would say Quizlet was an extremely useful tool before my exam because it helped me to consolidate everything that I've learned within the whole J2 and J1 life. Yes, so for most of you all, I'm sure there'll be like other commitments like CCA, outside activities. And y'all know it's important to study hard, but it's also important to play hard. So you must have a right balance between studying and CCA or like any other activities. So I'm sure a lot of y'all will be taking part in SYF or A divisions within these 2 years. And it's a really good experience, but then again, you cannot like neglect studies. Like I said, you do not want the accumulation of work. So you should always balance out and set some time off from CCA or like other activities to do your work. So like for example, before CCA or after CCA. Yeah, so I'm sure every one of y'all wants to avoid the snowball effect. So like say no to snowball effect. Yes, so you do not want your tutorials to accumulate and all your lecture videos to accumulate, because as y'all know, watching like 1 hour lecture videos constantly, like consecutively, can be extremely boring. So yeah, so my biggest tip for JC is whenever you're facing difficulties, ask your tutors, and also to have confidence in yourself and constantly do your work, and that should help you through JC and you'll struggle less. Let's not entirely avoid it all. Yeah. So that's it. That's all I have for now. So hopefully everything I've mentioned will be helpful in your JC journey. And yes, all the best and have fun. Okay.
Thank you, Wei Ling. Okay, so let's clap, right? Like she prepared a lot for this. Okay, let's clap, give her a round of encouragement, right? Thank you, Wei Ling. Anyway, she's receiving her A-level results very soon, right? So in Tuesday, right? Tuesday. Okay, so we wish you all the best. Okay, just a little bit. Wei Ling, right? She's always in my class, and almost every single lesson, I will ask her a question, and she knows it, right? She's always seated there waiting for when is Mr. William going to ask me a question, right? But every time I ask her a question, and she usually will get it correct. So she's a very nice student, a very hardworking student, someone very nice to work with. All right, so thank you for that. Okay, right. I tell you what, I'm going to give you guys a very small break of about 5 minutes because I know it's very content heavy today, right? So during this 5 minutes, you just stretch for a little while. So what I'm doing now is I'm showing a share screen, right? So there's this countdown for 5 minutes, right? So 5 minutes later, there's still quite a fair bit of contents to go. All right, guys, welcome back. Shall we continue? Okay, if you're back, just do switch on your webcam, right? So I know you guys are back, and then we can continue from here. Okay, thank you for that. Okay, come, let's continue. Okay, I still have quite a fair bit to go. Okay, I may have to cut a bit of things here and there, but I'll still get majority of the things done. All right, now we have understood ionization energy. All right, we have also seen graphs and trends to the question. Now, the next thing we're going to touch on is what really affects ionization energy. Right, you can see that there's one full page that kind of explains this concept called effective nuclear charge. Now, effective nuclear charge, short form, we call this ENC. Now, ENC is basically the net attraction of the protons for the valence electrons. Okay, you see, right? Imagine, usually, if you increase the number of protons, what will also happen is you will increase the number of electrons, And when you increase the number of electrons, you are likely to increase the number of shells. Okay, so you can imagine this. If you have a proton, all right, now as the proton number increases, just imagine this thing gets bigger and bigger. What will happen is you are likely to suck electrons in closer and closer. The proton is like a magnet that's constantly sucking electrons in. But do not forget, if you have more and more shells, then what happens is you will create more and more layers. And because you create more and more layers, the layers will prevent the attraction. It will weaken the attraction. So there's a double-edged sword. On one hand, you increase proton, that means you increase the suction. But on the other hand, you increase the number of shells, that means you would decrease the suction. All right, so you must understand that there's this problem that we exist, right? So number one, it is the nuclear charge, right? Nuclear charge is basically the attraction between the protons in a nucleus as well as the valence electrons. So every time nuclear charge increases, it is a result of an increase in proton number. So you can write down, this will increase attraction, all right? It will make them closer together. But at the same time, do not forget there's a shielding effect. Now, shielding effect basically is this. You can see a picture on the right-hand side of your notes, right? Every time you have additional shells, what the additional shells will do, for example, the one I'm shading right now, this shell is going to block, right? It's like a layer of blockage. It will make it harder for the nucleus to want to suck in the valence electrons. Then that effect is called the shielding effect, right? So the shielding effect of the valence electrons from the nuclear charge as a result of repulsion from inner electrons. So the more inner electrons you have, the more repulsive effect there will be, and it becomes harder for the valence electrons to be attracted to the nucleus. Okay, so you can see it will increase with an increased number of inner electron shells. And bear in mind, there's negligible shielding from electrons in the same shell. All right, so shielding effect typically works when you're looking at inner shell of electrons. You cannot say, for example, this electron is shielding this electron. You cannot, because they are in the same shell. You must be in front of the valence electrons in order to shield it. Okay, so shielding effect decreases the attraction. So what is ENC? Now, ENC is simply a balance of the two factors. It usually turns out one effect will outweigh the other. So there's like a formula. You don't need to memorize this. We'll never test you as a formula. But basically, it's a balance of one after the other. All right. So it says below, now there are three properties that will reflect the effective nuclear charge. Number one is called ionization energy. We just learned it. Number two is radius. And number three is electronegativity. Now, all these guys, they are all related to size. Okay, which I'll explain to you in a short while. Okay, I need you to flip over. This is probably very new to every one of you guys. Okay, some graphs that you must get used to, right? So we flip over to this page. Now we look at trends of atomic properties in the periodic table, right? Look at the axis here. This is the first IE across atomic number. Now, when you look at this graph, initially people will get confused with what we have done earlier on. Now, if you flip a few pages back, okay, for example, if you flip back to this particular page, 124, can you do it right now? You go to 124 very quickly. Now, you must realize that in that kind of question, what we are doing is we are doing successive IE on the same element. So that means you remove the first, the second, the third from the same guy. But what is happening right now is we are not removing from the same guy, we are removing from different guys. And I'm only doing the first IE, only removing the first electron from different guys. All right. So what you should do is you need to break this down in your periodic table. Can we label? This is period 1. All right. Then this portion here is period 2. And this is going to be period 3. Now, all I need you to do is to focus within one period, right? Just focus within one period. So we're going to fix our eyes on period 2. The trend is the same as period 3, right? So let's use period 2. What you notice is as you move across a period, right? You look at your data booklet or periodic table, these are the species you have across the period. The trend for first ionization energy is it is going up. Okay, it is going up. But I say again, do not confuse with what we have done previously. It's totally different because I'm removing from different elements, not the same element. All right. Now, as we go up, but sometimes you see that there are dips. Can you see like there's a dip over here, right? Can you go and circle the dip? Let's do it together, right? This is a dip and this is a dip. Okay. So if you look at your sequence, right, this is in group 1. This is in group 2. This is in group 13, then 14, then 15, 16, 17, and 18. So this will be the sequence of the elements that's in period 2, and the whole thing is going to be repeated in period 3. So you do notice the trend is going up, but sometimes there are small dips. And where do they dip? Did you notice? It will dip at group 13, it will dip at group 16. Okay, so the shortcut way for you to remember, first IE, the trend is it will go up, but then for some reason, it will dip at 13, it will dip at 16. Okay, write this down for yourself. 13, 16, it will dip. I will explain to you why in a short while. Okay, now something that's also a bit linked to your secondary days, but you may not be very familiar, is how the size change across a period. Okay, so you can imagine, let's say this is period 2. Does the size get bigger or does the size get smaller across a period? I'll tell you the answer. Size always gets smaller across a period. Okay, so I like to draw this picture to explain the first member is usually very, very big. Then as you move across the periodic table, the last member, it tends to be very small. Okay, so make a note for yourself. Size will decrease across the period. Okay, so we use logic. If size were to decrease across a period, now you can imagine this is my nucleus and this is my nucleus. This guy is trying to suck in electron. And then this guy is also trying to suck in electron. Does it sound logical that this attraction is going to be stronger? Because the electrons are closer to the nucleus since the entire thing is smaller. And then this attraction is probably going to be weaker. So if the attraction is weaker, that means the electrons must have been easier to remove. And if electrons are easier to remove, it will mean that it must have lower ionization energy. So this will explain the trend, right? Why size decreases across the period results in stronger attraction, and therefore IE will start to increase because you need more energy to remove those electrons. Okay? So if you're with me and you understood what I'm saying, you can see below, right, the trend. Okay, let's take a look. We just highlight certain things. I need you to take note of your presentation. Okay, the way you present, super duper important. There are 3 things we'll always write. The first thing we explain is the nuclear charge effect. So when you move across a period, if you look at the periodic table, you must expect the proton number to increase. Okay, so you will say nuclear charge will increase because proton number increases. But as you move across a period, you do not increase the number of shells, right? They are within the same period. So you must explain shielding effect is approximately constant. Reason being, electrons are added to the same valence shell, right? And the number of inner electron shell will remain constant. The reason why we say number 1 and number 2 is because we need to link back to the concept over here, right? Not this, okay, but over here. ENC is the net balance between these two guys. So in every presentation of your answer, you must mention how nuclear charge changes, you must mention how shielding effect changes, and then you strike a nice balance between the two of them. Okay, so your presentation, like I say, is super important. Okay, so after you're done with this, then the third thing you mention is the balance. The balance is the ENC. Because shielding effect didn't really increase, but proton number increases, so I'm expecting a stronger attraction, right? And the end result is valence electrons are more tightly held to the nucleus and more energy is needed to remove those valence electrons. And that's why first IE will generally increase. Okay, this is to explain the pattern. Why is it going up? Okay, now we need to explain the anomaly. Anomaly means the exception. Why are there dips occurring between group 13 and why are there dips occurring in group 16? Okay, the best way to actually answer this is to use electronic configuration, right? Write this down. Anomaly is always explained by electronic configuration. Okay, so remember, right? We usually expect the whole thing to go up. But then when you move to group 13, there is a sudden dip. Okay, how to explain? You always write the electronic configuration. And then you notice beryllium is someone that is in group 2. Okay, boron is someone that is in group 13. So if you think about the electronic configuration that beryllium has, beryllium will end with a 2s2. Boron will end with a 2s2 followed by a 2p1. Okay, so you must realize, what is IE? IE is to remove the valence electron, the outermost electron. So if you ask yourself this question, is it easier to remove from the 2p or is it easier to remove from the 2s? It's always easier to remove from the 2p because the 2p is further away from the nucleus. So the main idea is this: these electrons are easier to remove. Because it's easier to remove, it will correspond to having a lower ionization energy, which is not quite expected because we expect the trend to be going up. All right, so you can see the way that you phrase it is very important. You must mention the first IE of boron, right? So this is boron. The first IE means I'm going to remove electron from the 2p orbital, while the first IE of beryllium, this is beryllium, I will still be removing electron from the 2s orbital. So to remove electrons from the 2p, you're going to require less energy to do that because it's further away from the nucleus. It is also higher in energy as compared to the 2s electron. Okay, so long story cut short, you must be able to explain the concept for this. Why is there a dip? Okay, and the reason for a dip is because the moment you go to group 13, you must start filling the 2p orbital. Once you start filling the 2p orbital, because those electrons are easier to remove, that's why IE will drop. Right? So write this down. The concept is a change in subshell. From the S subshell to the P subshell. That causes the dip. Okay, now we're going to build on this on the next page. Now the next page is to explain the anomaly between group 15 and group 16. All right, so group 15, we have nitrogen, and group 16, we have oxygen. So when you write the configuration of nitrogen, you will notice this guy is 2s2 with 2p3. Then oxygen is 2s2 with 2p4. Now your focus is on the p orbitals. So when it's 2p3, what will happen is electrons will be singly filled. But the moment you have 2p4, okay, remember what I mentioned just now? Electrons originally will be separated. Then later, they will be grouped together. So can you see the moment you have P4, what are you introducing? You introduce 2 electrons within the same orbital. When you have 2 electrons within the same orbital, it creates this effect called interelectronic repulsion. So that repulsion is not very stable. All right. So you can see interelectronic repulsion in one of the 2p orbitals of oxygen. So what it means is the whole thing becomes unstable. So once it's unstable, you have less energy that's required to remove the valence electron of oxygen as compared to nitrogen. Okay, so if you consolidate and you truly understand, the reason for this dip is not the same as the reason for this dip. This dip is because you go from the S to the P subshell. But this dip is a result of going from P3 to P4. And the moment you have P4, you start to introduce interelectronic repulsion that will destabilize the entire system. All right, so what is the concept? Now, the concept is you have interelectronic repulsion. Okay, now if you're okay with this, I need you to go back to the graph together with me. Okay, shall we do that? Let's go back to the graph. Now, when you look at this graph, okay, I'm going to write down the configuration together with you. You need to do this with me. Okay, this guy, his configuration is S1. Okay, this guy is S2. This guy is S2P1. And I've explained to you, the moment you reach P1, there will be a dip because electrons are easier to remove. Okay, then after which you have here S2P2. This is S2P3. This is S2P4, S2P5, and finally you have S2P6. So the moment you have P4, there is also a dip because of electronic repulsion or interelectronic repulsion. All right, so this is going to be the graph of, take note, only the first ionization energy, the first IE. Right? And I'm going to show you questions first. Okay, then we're going to build on this and we start to look at things that can be quite complicated in a short while. Okay, but we first look at the question below. Can you flip to the next page? Okay, follow me. Okay, now in this question, the question is asking, I'm giving you the first ionization energy of 7 consecutive elements in the second and the third period of the periodic table. So they ask, what element might A be? Okay, so if you have a periodic table, take a look, right? Focus on period 2 as well as period 3 of your periodic table. Okay, then you notice something. As you move across, the general trend is that IE is going up. It is going up. But suddenly, from here to here, there is a huge dip, right? A huge dip. Can you see that? Okay, so when does this dip happen and what is the reason for this dip? Okay, you see here, I will show you a periodic table. Okay, digest this with me. If we are going to move across a period, okay, let's focus on period 2. We understand the general trend is always going up. From someone that is group 1 to someone that's group 18, the general trend is going up. Of course, there are some dips in group 13 and group 16, it will dip, but generally the trend is going up. But don't forget, right? After you're done with the first, second, third, fourth, fifth, sixth, seventh, eighth, what happens to the next guy? Now, the next guy is going to be in a new shell. And the moment you go into a new shell means your electrons are definitely further away from a nucleus. These electrons are definitely way, way easier for us to remove. So the only time you see a huge dip is you go from a noble gas onto the next period of a new quantum shell, right? Or the next row of a new quantum shell. All right. So the message is this. When you look from here to here, okay, here to here, there is a huge dip. What does that mean? It means that this guy must be group 18 and this guy must be group 1, but of a lower period or a new period. Then this guy must be group 2. Okay, so once you recognize, okay, this guy is group 18, you can actually begin to work backwards. You can try, this is 17, this is 16, this is 15, and this is 14. Okay, how can you be double sure? How can you confirm that what you have done is correct? Okay, remember the trend for first IE, it is always going to go up, but where does it dip? It will dip at group 13, it will dip at group 16, right? So we use the data here. Can you see? Just nice. Group 16, there is a small dip. So my suspicion is being confirmed, right? Because there's a dip on group 16. I do not have information about group 13, but it does seem to suggest everything falls into place. Okay, so you want to use this to actually approach and solve for the question. All right. Okay, so what I would do is I will not go through every question. I will just give you the idea how you approach the question. So once we know what groups they are in, just look at period 2 and period 3. You'll be able to figure out A is carbon. Okay, then you just basically copy the information from the data booklet. Okay, all right. Now, so I have done already part 1. Okay, just one bit. Why is it that the IE of C is smaller than that of B? Okay, so what are they referring to, right? C, as you can see, is oxygen. Then B is going to be nitrogen. So why is it oxygen has a dip, is smaller than nitrogen? The concept is interelectronic repulsion. Because you go and write the configuration, right, you will see that nitrogen ends with a S2P3, but oxygen ends with a S2P4. So every time it's group 16, from the graph you saw just now, the answer is always interelectronic repulsion. Okay, now I'll do one more question with you on the next question, question 2. Okay, let's flip over to the next page. All right, now in this question, I just need you to try this one. Okay, it says that I have 3 different elements. So which of them will show the correct sequence of the first IE? Okay, so same thing, I'm going to bring out a poll question. When you are ready, you just let me know what is the answer to this. I just want to make sure everybody you're on track. Okay, good. Quite a number of you guys are done, right? So I'll share the results. Most of you guys chose A, and congrats, A is the correct answer. Okay, now for those who got it wrong, right, that handful of you guys, maybe a few things that you might have overlooked, right? So you can see the question here is asking for the correct sequence of the first ionization energy. So if this is the most endothermic, it means that it must be the hardest to remove. All right, and the least endothermic means it must have been the easiest to remove. So what you need to do is you really need to look at your periodic table. Okay, I'm just going to go to the periodic table on the previous page. Where are these species? It's here, radon, francium, and radium. All right, so you can see that this guy is in a previous quantum shell. So in a previous quantum shell means it must be a lot harder to remove this. This must be the hardest to remove. They are closest to the nucleus. All right. Then between francium and radium, your thoughts will be IE generally increases across the period. So I must be expecting the ionization energy of radium to be bigger than that of francium. All right. So that's the reason why we end up with option A as the answer, right? So just take note, this must be the most difficult to remove. Then between these two guys, IE will increase across the period. So this one must be harder to remove as compared to francium. Okay. All right. Now, question 4 and question 3 and question 4, I will give you the answer. Okay. You can try it yourself. Then I'll touch on a few more stuff. Question 3, the answer is C. Then question 4, the answer is B. Okay, you can try it. If you're not sure why you got it wrong, when you come back to class, you check with us. We'll explain to you the answer behind this. Okay, but question 3, question 4 is dealing with second IE. Just take note, not first IE. So when you're doing second IE, you must bear in mind that you are removing the second electron, not the first electron. Okay, so for example, if you choose this, you must bear in mind you are not doing this to 1s2, 2s2, 2p6, because that only represents the first ionization energy, right? What you are doing is you are doing the second ionization energy. So you must be trying to remove electrons one more time to end up with a 2p5, right? So you have to kind of like bring forward to one more step to do the second IE. Okay, go try it, digest it. Not sure, it's okay. You come back, we'll explain to you. All right. Okay, now just give me a bit more time. Okay, I know it's a little bit late. Okay, I'll try to finish ASAP. Okay, max 10 minutes. Okay, give me the next at most 10 minutes. I'll try to finish this. Okay, now the next thing we will touch on will be atomic and ionic radius across the period. Okay, this one we can go through very quickly because I've explained to you how radius will decrease as we move across a period. It will get smaller as we move across a period. So this is represented, as you can see, period 2, it gets smaller. Period 3, it gets smaller across the period. And what is the reason for that? We have also touched on that earlier on, right? We explained as you move across the period, what will happen to the proton number? As you move across the period, the proton number increases. But you don't increase the number of shells, so the shielding effect is approximately constant. So you present this way, talk about the nuclear charge, talk about the shielding effect. Then the last thing you do is you give a nice balance, a balance of effective nuclear charge. Okay, so this one is, I've done it, so I will skip this portion. Okay, I want to touch on the next one. Okay, this will be the almost the end already. Okay, so you take a look at the next one. Okay, this portion is variations in ionic radius. Now, just now was atomic radius. Now is ionic radius. Okay, so when you're dealing with ionic radius, you must first look at the atomic radius. It will be decreasing across the period. All right. Then when it's ionic radius, you must take note that these three guys is always going to be cationic in nature. But the rest of them is going to be anionic in nature. Okay, now silicon is a little bit special. It can be both cationic and anionic at the same time. It can be either way, but some of them are always going to be cation, some of them are always going to be anion. All right, so you notice the difference between cations and anions is if you are anions, you will be gaining electrons. If you are cations, you will be losing electrons. So in the case of cations, they must lose away the entire shell of electrons. You must take note, right? So cations will usually have one shell less. Anions will usually have one more shell. So that's why you can see, right? Generally, the anions, they are larger, and then the cations, they are smaller, okay? But that's one thing. You must also be able to explain how come the trend is decreasing this way, okay? Why does it work this way? Okay, one trick that I can share with you is to do this, right? You will consider the ratio of protons to electrons, okay? Learn this, the ratio of protons to electrons. Okay, you can see, right? When there's sodium plus, magnesium 2 plus, and aluminium 3 plus, they all have the same number of electrons, right? You go and count, when it's Na plus, you will notice that sodium has 11 protons, but because you remove one electron, now there are 10 electrons. Okay, then magnesium, they have 12 protons, but because you remove 2 electrons, they have 10 electrons. All right, and same thing for Al. Al has 13 protons, but they have 10 electrons. So the key thing that you must note, right, is all these guys, they happen to have the same number of electrons. We call this isoelectronic, right? Same number of electrons. Okay. Now, if you have the same number of electrons, the problem is this. Imagine you have protons, and the job of the protons is to suck electrons in. All right. Now, if they all have the same number of electrons, but some of them has more protons, so the one with more protons will naturally have a stronger suction, right? He will bring the electrons closer together. He will decrease the radius. So what I need you to do in exams, right, is you list down the respective number of protons to electrons. The proton is the one that sucks the electrons in. So the more protons you have, I'll label here, you will be able to have a stronger attraction. And a stronger attraction will mean you are going to have a smaller radius. All right, now the same idea works for P3 minus to Cl minus, right? If you consider the number of protons to electrons, you will see that phosphorus has 15 protons. But because it's a 3 minus, it will end up with 18 electrons, right? Then for sulfur, 16 protons and 18 electrons. Then in the case of chloride, it will be 17 protons and 18 electrons. So for the same number of electrons, what happens is this guy, because it has the greatest number of proton, it will have the strongest attraction. And therefore the radius will decrease. Okay, so when you do questions, it's a very useful trick. You just consider how many protons to electrons you have, then you will know who has stronger suction, and the one with the strongest suction will give you the smallest radius. Okay, all right, so the phrasing, as you can see, all right, how do you explain is you explain there's an increase in proton number. The nuclear charge increases, but the shielding effect is it's going to remain constant because you have the same number of electrons. So therefore, they have stronger suction, or there is an increase in effective nuclear charge, and therefore the valence electrons are more strongly attracted to the nucleus. Okay. Something we have also mentioned, the radius of the anions are always bigger than that of the cations because of the additional shell. Okay. All right. Now, this question, how do you do the answer? Who has the largest radius? Who has the smallest radius? You go and check the ratio of protons to electrons. Okay. You go try it yourself. I give you the correct answer. The correct answer is C. Okay, last thing. Okay, then we are done. Okay, and last one is very, very fast. Okay, you flip over to the next page. Okay, over here, this one no need to explain. You will know it for sure. How does radius and first IE will change as you go down the group? Okay, so if you look at your periodic table, the moment you start going down the group, what will happen is you have more and more shells, right? So every one of you guys will know, at first you got one shell, then 2 shells, 3 shells, and 4 shells. So if I expect the size to get bigger, can you see that? The radius gets bigger. So with a bigger radius, then what it means is the electrons will be more loosely held to the nucleus. And then these electrons are going to be easier to remove. So that's why the ones with the largest atomic radius will correspond to the lowest ionization energy. Okay, so the explanations is more or less the same. You mentioned that as you go down the group, although the nuclear charge increases, right, shielding effect increases, but the key idea is this: the valence electrons, they are further away from the nucleus. So like the picture I've drawn here, so it means that the atomic radius will increase. So the valence electrons are less strongly attracted to the nucleus, and you need less energy to remove those electrons. All right. Okay, so your last question, again, you go and try this yourself. The answer to the last question is going to be donkey. Okay. All right, good. The last page, you can read this yourself. It's not very difficult. It's on electronegativity. Okay, so I want to consolidate very quickly, right? In this chapter, okay, what is important is your spdf. You must be able to write the notations, right? You must understand the sequence of filling up, all right? Then the next thing that's important is the graph of ionization energy. You must be able to draw the graph, whether are you removing from the same element or you're removing from different elements. We talk about the different examples and the different ways to draw the graph. You must make sure you master this. Okay, now in the chat, there were a lot of people asking the same few questions, right? Okay, so I'll just reply at one go. Okay, so some people are asking, when are we starting chemical bonding? We're starting chemical bonding this week in our classes, right? So this entire week, we started on chemical bonding, which is the major chapter. So if you're asking that question, that's the answer, all right? Then some of you guys are asking which classes are still available. Okay, so I'll just be very quick. I'll skip all the stuff, right? Okay, I'll just talk about this. All right, so these are the classes that is available right now. Okay, so what I encourage you to do, right, if you're a bit unsure whether you want to join a tuition or not, then the best thing you can do is maybe you want to come for a trial lesson. right? So you can contact the enrollment specialist, right? This is the number over there. So you can say, I want to book a trial lesson. I want to see how is it like, because Zoom and the actual session may differ a little bit. So if there's something that interests you, right, send a text to the enrollment specialist. If you can make it tomorrow, I can tell tomorrow is the best time to do a trial, because tomorrow is a brand new chapter on chemical bonding. It's a chapter that you probably will struggle a lot with, right? So like I mentioned, we're not pushy. We just tell you what we have, right? We give you a sample of our lessons. If you find that we can work together, we'll be happy to help you. If not, it's okay. At least we taught you something in atomic structure. All right. So if you have any other questions, you can feel free to stay behind and check with us, right? If everything is good, then you probably will need time to consolidate and read through. So when you come back to class, just feel free to ask us questions. Okay, so for those who are okay, right, thank you for attending the class. I'll see you guys back in class next week. Right, for those who have questions, just feel free to stay behind. All right, bye-bye.
Thank you. Bye.
Yep, thank you, bye.
Teacher,
Yes.
I got a question. On page 125.
Yep.
When you talk about the ionization energy, right? Do you look at the dots or the line?
The dots or the lines?
Yeah.
The line is the connection. So this is the first IE, second IE, third IE, fourth IE. The line is to show you the trend.
Okay. And then right, the seventh ionization energy. That means like it's when the very high increase, right?
Yeah. First, second, third, fourth, fifth, yeah, sixth, and this will be the seventh.
Yeah. The high increase is because like the electrons removed from the inner quantum shell, right?
Yes, you're right.
Then but I thought like the quantum shell remains there. Like you just remove the last electron from the valence shell.
Okay, so if you have this, after you remove all the electrons here, the next one you remove will be an inner shell. So it's going to be harder to remove those electrons.
Yeah, but then they ask, why is there a huge increase from like the sixth to the seventh ionization?
Because the seventh belongs to the inner shell, so they're trying to tell you that this is harder to remove. It must be because you're in the inner quantum shell, so that's why it's harder to remove, and that's why there is an increase.
So the question is, they are asking you to compare between the sixth and the seventh, like the ionization energy, and then basically they're asking you to compare like the sixth ionization energy, right? Why is it so high, and then compare it to why the seventh one is smaller, is it?
They didn't ask you to, yes, I mean, in this part, they're asking why is it there's a huge difference from the 6 to 7? And the only way to explain why there's a huge difference from the 6 to the 7 is because there's a change in quantum shell.
So do we talk about like the electrons being removed from the valence or like from the inner?
What do you think? If I'm much higher, is it from the outside or the inside?
The outside.
If it's outside, is it easy to remove, or inside is easy to remove?
Outside easy to remove.
Yeah, but now it's difficult to remove. This one is a huge increase. So this one is a lot more difficult to remove. So are you still outside or inside?
Inside.
Yep. Okay. So that's the idea.
So if you but then if you just remove like the last, for example, the last electron in the valence shell, right? That means it'll be easier to remove, is it?
Outside is always easier to remove. Inside is always harder to remove. Because inside is closer. There's stronger suction.
Okay. Okay. Yeah.
Can?
Yeah, and the shielding effect, right?
Yep.
I'm not like 100% sure what they mean by negligible shielding from electrons in same shell.
That means if you have the first electron here, and then the second electron here, this electron and this electron is in the same shell, you cannot say this guy is blocking you. You know, it's the same idea. Yep.
So it's only different shells then.
It's the same idea as you come for class, right? Imagine I'm always standing here, then there's one student seated here. If you're seated behind the student, only the student in front can block you. If a student is sitting beside you, the student is not blocking you. So only the inner shell is blocking. Same shell is not blocking.
So basically like the okay, yeah, I get it.
Okay. All
Okay.
right. Okay, thank
And
you.
also one last thing, right? The interelectronic repulsion also not quite not quite understand.
That means the moment you have two electrons in the same orbital, they will repel each other. Electrons are
Okay.
all negative. So having two negative in the same orbital is not a good thing. So that will make it unstable.
Okay.
Yep.
Wait, that's it.
Yeah, that's it. Lah.
Oh. So like for example, like the page 128, the question 1, right? Like part 2, they ask why the ionization energy of C is smaller than B. Like then how do you explain like using the repulsion?
So when there's repulsion, then it's not stable. So it's easy to remove those electrons.
Oh, all right. Okay. Yeah, I get it.
Okay, thank you. Okay, the rest of you guys, any other questions? I'm here.
Mr. William, I want
Yes.
to ask, right,
Hmm.
for page 126, the question 3.
1, 2, 6. Okay. Wait. 1, 2, 6. Yep.
Why is it like, why do we only look for one significant jump? Because like from the second to the third for the X, right? Second to the third ionization energy is like a relatively big jump compared to the first to second, third to fourth. So why can't there be one significant jump? Then the other significant jump is from the fourth to the fifth.
Okay, so if you say, you think about a shell, right? So a shell, let's say the configuration, maybe it's like 2, 8, 5, let's say, all right? So if there's a jump, it means that you're going into a new shell. Now the new shell must have 8 electrons inside. So what you're trying to say is, oh, there is a jump here, and then there's, where else there's a jump?
The fourth to the fifth.
The fourth to the fifth. Okay, that means you're telling me that this belongs to one shell. Does it sound logical?
Oh, okay.
All right, so you must have 8 electrons in one shell minimum. So yes, you're right. Yes, you're spotting some jumps here and there, but it cannot be everywhere there's jump because every electron or every shell must have 8 electrons. So it's only logical you look for the biggest jump. That will be the one that makes the difference.
So if they show like 9, 10, 11, 12 ionization energy, then there might be 2 jumps.
Yep, you're right. It's possible there might be 2 jumps.
Okay. Wait, then if like from the graph, right, if the graph is first ionization energy, then they ask you to plot the second ionization energy, then like, is there a way like on how to plot it?
Okay, as a quick guide, first IE, it dips at 13 and 16. And then the second IE, it will generally dip at 14 and 17. The whole graph will shift to the right by 1 unit.
Oh, but how do you know what does it start from? Like what is the starting element?
No, it's always a relative thing. So it's always relative. That means it doesn't matter where you start. So let's say you just anyhow start here. Then after that, you just keep going up. Then the moment it is group 14, it will start to dip. Then 15, 16, 17, it will start to dip. So all you need to see is that the graph is always going upwards. That's all we need to see.
Oh, then like in order to identify like the group of the first dot, you see like you find the biggest jump, then from there you calculate like how many electrons are there. Then from the number of electrons, you know that is the group number because like electrons, there's the valence electrons, right?
Yes, something like that. So it's very similar to the data here, whereby you look for the biggest jump.
Okay, I get it.
Okay.
Okay, thank you.